Universities. Mr. Professor, our group is yours, and I hope that we will have a very pleasure to listen to you.
Thank you very much, Professor. Good morning, everyone. As you heard, my name is Optical, and I'm so glad to be here. I think I've walked around a little bit of the city, and I think it's a very lovely city. And we were here yesterday, walking around the campus, and I think it's very lovely. So thank you so much for having me. I'm going to give a talk about what I do in terms of research, and I hope you're going to find it interesting. During my talk, you are free to ask questions. You don't have to wait till the end. You can stop me, you can ask questions, and I think that will be very good. I highly encourage that as we go along. So, first of all, I want to appreciate the university and the European Union for sponsoring my visit to this university. My name is Dr. Popular. I'm currently a lecturer and Chancellor's Fellow from the University of Edinburgh. My email address is there, and that is my webpage. I'm in the School of Engineering, and my institute is Institute for Digital Communications. I also belong to the Li-Fi R&D Center. That is a center that is mainly for optical wireless communications in the University of Edinburgh. I think it's the biggest in Europe as we speak in terms of optical wireless communications research. So in terms of outline for my talk, I'll talk a little bit about my university, and then I'll talk about my research for the rest of the talk. It should be 40 minutes, 50 minutes, thereabout, and we have plenty of time for discussion. So, my university, the University of Edinburgh was started in 1583, many years ago, 1583, and it's in Scotland, the capital of Scotland, the Edinburgh city. It's not this warm, okay, but it rains a lot in Scotland. We have about 36,000 students, and this is the breakdown of the students. Some of them undergraduates, some of them masters, MSc, and then the rest are PhD. So you can see we have about just over 4,500 PhD students. Our masters, over 7,500, and undergrad, about 23,000 students. So that's everything, just about 36,000. We have 3 colleges, and my college is College of Science and Engineering. That is my college. But within the college, we have schools. Right? So we have 7 schools in the college. So my school is School of Engineering. In engineering, we have 150 academic staff, I'm one of them, and we have 350 PhD students in the school, 140 MSc, and 1,400 undergraduate students within the School of Engineering. Within that School of Engineering, we have institutes for research, right? Here in engineering, we cover all engineering, civil, mechanical, electrical, electronics, power, everything. But they are divided into institutes. These are based on research. These are based on research. So people that do bioengineering, biomedical, biosensors, they belong to this institute. This is an institute for energy systems, renewable energy, power electronics, machines, and so on and so forth. They belong here. And this is infrastructure and environment. This is a bit of civil engineering and a bit of mechanical as well, infrastructure and environment. This is integrated micro and nano systems. It's part of electronic engineering, but they do devices, some of them photonic devices, microelectronics as well. So that's that institute. And then we have materials and processes. This is mainly chemical engineering. And this is my institute, which is mainly electronic engineering. So this is where I belong. So within that institute, our research is mainly in 3 areas: communications, signal processing and image processing, and tomography. So in comms, we have radio frequency, mobile, wireless, and so on. We also have optical communications, and that's my research interest within the group. So there are 3 academics in optical communication. 3. We have 1 professor, and then we have 2 lecturers, myself and another colleague. So we can 3 in optical communications. So that's that. We have 15 altogether in my institute. 40 postdocs. These are PhDs doing just research. And then we have 80 PhD students. within that institute. And again, we do world-leading research from theory to practice to application. That's what we do in the institute. So, now to my talk. My talk is going to be on multi-carrier modulation in optical wireless communications. What is multi-carrier? Why is it important? You have a question? Okay. So what's multi-carrier modulation? Why is it important? What do we use it for? And what are the challenges there? So that's what I'll be talking about this morning. So multi-carrier modulation is basically frequency division multiplexing. That is, you have different frequency for different data, and then you add them together. That's essentially what it's all about. Here, I've got a diagram. This is one frequency, this is higher frequency, even higher, and so on and so forth. This low frequency is one data. This next one, another data. Next one, another data, and then you add all of them together. So it becomes frequency division multiplexing. So that is essentially what MCM is all about. This is another illustration. You have your data coming in, you convert from serial to parallel. They all go parallel together. And then you give one to this carrier, another one to the second carrier, another one to the third, and so on. And then you add them all together to form a composite signal. So that is multi-carrier modulation. You can put guard bands between them. That is, you've got a carrier, let's say this is frequency scale. So I can put F0, that's one data here. I can put another one, F1, another one, F2. Between F1 and F2, I can put a guard band. There's nothing, just an empty slot, just to make sure there's no spill. Energy from here doesn't spill to this one. We want to avoid interference. So we can put guard bands in between them. F1 and F2 can be orthogonal. They don't have to be, but they can be orthogonal, such that if you do the product of these two, the convolution of these two, or the correlation, it should be 0. That's why we want them to be orthogonal, okay? So that we don't want any crosstalk between them. It doesn't have to be. If you do that, then it becomes what is called OFDM, orthogonal frequency division multiplexing. Orthogonal because the subcarriers are orthogonal. If this is F0, this will be 2F0, 3F0, 4F0, and so on. Multiples of the fundamental. And then if you do that, it can be implemented in DSP very easily, and also in MATLAB. That is why nowadays WebGen is very attractive, because when it comes to implementation, it's dead easy in MATLAB. Just do IFFT and FFT, and that's it. Many processors, like Arduino, like FPGA, some of them have this block there, FFT inbuilt, so it makes it very easy to do. And if you use sync pulse, that is, if you use rectangular pulse in time domain, it becomes sync pulse in frequency. So you cancel any interference. That is, if you sample here, at this point, you only get the red, nothing from the other ones because they are 0. And then the next sampling instant, you get just the green, the red is 0, the blue is 0. Right? So that is why it is good to make it sync pulse in frequency domain. So you have no interference. That is, in a nutshell, what OFDM is all about. Now, why is it important? Why do people do OFDM? Why do people try to study it? Well, one of the reasons is because it's robust to channel feeding. This is general, not just for optical wireless. People use it in radio as well, in mobile, in DSL, in broadband. It's used, but it's because it's robust to channel feeding. There's no intersymbol interference, as I explained, because the subcarriers are orthogonal. So there's no crosstalk between them. Also, it can increase capacity with OFDM. Why? You just keep adding more subcarrier, and that means more data. For as long as you have enough bandwidth, then that's also an advantage. And then it's very easy to implement in DSP using FFT or IFFT blocks. And then if you have problem in the channel, which is always going to be there, you can do equalization at the receiver. And that is very easy with just one tap. That is, you do zero forcing, single tap in frequency domain. And that's why that's also it's a good thing. It's very simple to do. In radio frequency in wireless, it's being used in digital audio broadcast, DAB. It's used in TV, digital TV. It's used in broadband. It's used in wireless LAN, WiMAX, mobile, everything. They use OFDM. Now, it's implemented. In optical, it's using optical fiber communications, using radio over fiber and optical wireless. And that is the one I'm going to talk about today, optical wireless communication. But that's my research area. Okay? So optical wireless. Well, until recently, optical communications is all about fiber communications. It's all about fiber. But now, we have advances in optoelectronic devices. We have better lasers, we have better LEDs, we have better detectors. So, that means we can now do fiberless communication. It's essentially identical to fiber communications, except that we take away the fiber. So it becomes traveling or sending light to free space, essentially. So we can now use optical wireless for outdoor, for terrestrial, for indoor, for underwater, and even space. As we speak, there's one laser link in space by European Space Agency for transporting huge amount of data. That is operational as we speak. Okay, so it's taking off. So it comes under different names. Optical wireless communication. Some people call it fiberless optical communication. Some people call it laser communication. Some people call it free space optics. All these three, they mean exactly the same thing. And essentially, these three, they are for outdoor application of optical wireless. So when it is outdoor, people call it laser communications or free space optics, right? When it's indoor, then it can be called indoor infrared communications or visible light communications or Li-Fi. Now, this is infrared, that is beyond what the eye can see, from about 780 nanometers wavelength up. Okay, so that's infrared. If it is within the visible, that is from about 380 nanometers to about 700 nanometers, then it becomes visible. I'm talking of the wavelength of the source. So that's visible. Visible, VLC or Li-Fi, they mean the same thing, right? Actually, the word Li-Fi came from our university. The director of our research center coined this word, Li-Fi, from Wi-Fi. Wi-Fi is radio, then Li-Fi is light, that's where it came from. So that's the other names for it. So what are the differences between RF, radio frequency, and optics? Well, essentially, this is a key one. In RF, the signal is on the electric field, on the amplitude. In optics, no, it's on the intensity. We modulate our data on the power of the laser or the power of the LED, if you like. If you are doing incoherent. For fiber, you can do coherent. You can put it on the field, but we're talking of optical wireless. Essentially, it's on the intensity of the light. And for RF, it can be complex valued. You can multiply A plus JB. But in intensity, no. It's got to be real valued. It has to be real, no complex at all. And here it can be bipolar, positive and negative. But in optics, incoherent, no. It has to be positive only. Why? Because the output from an LED or from a laser is positive power, optical power. There's no negative optical power. So that's why it can't be negative. It has to be positive. And those ones, those conditions, put some constraint on the design of the system. So I've explained all of that. So the applications of multicarrier modulation, and I'm going to give my examples are going to be based on VLC. There are other examples for infrared, but my focus here is going to be on VLC, the applications. So why is it used? Well, if you use underwater, it's to mitigate dispersion in underwater, because when you send laser beam underwater, you have scattering, right? And you have dispersion. So you can use OFDM or multicarrier to correct for that. You can also use it to increase throughput in underwater, because the bandwidth is also very limited in underwater. For up, you can use multicarrier to fight against scintillation. Scintillation is when you have intensity fluctuation of your signal, right? So you can use multicarrier to correct for that. In indoor, Optical wireless for VLC and for Wi-Fi. Well, for Wi-Fi or VLC, the light source is LED, and that is also the illumination LED. They have very small bandwidth, and the bandwidth is non-flat. So those two, they represent a huge challenge. The response is not flat, and the bandwidth is so tiny. So to fight those two, we can use multicarrier modulation or OFDF. We can also use it for these two effects, but I'm not going to talk about these two. I'm going to talk about these first two today because of time. Right? So for VLC, visible light communications, we have a light source here that illuminates the room. And at the same time, we can send data through the light source from here to the laptop. And then we have maybe infrared that goes back up. That is visible light communication. The key thing is one light source for two things, for illumination and for wireless data. The spectrum is between 400 to 700 nanometers, and the radiation is visible. It's also for lighting. That comes with some challenges. Why do we do it? Well, advances in optoelectronics to solid-state lighting is very popular. Nowadays, you can't buy incandescent anymore. They are no more. The incandescent light bulb, they are no more. But you can only use solid-state lighting, like light-emitting diodes for illumination. They are the future. So because they are going to be there anyway, it makes sense to add data on top of them, right? For instance, if you buy an LED lamp, the life expectancy is about 20 years. It's going to be there, if you buy a good one, it's going to be there for about 20 years, right? If you think about the manufacturer, that means 20 years, no income for the company. So it makes sense to change their business model and then add something on top of the light. Otherwise, it's not going to be profitable for the company. So that's why VLC is an attractive proposition for LED manufacturers as well. Huge unlicensed spectrum. The spectrum is free, it's not licensed. Then there's congestion, as we all know, in radio frequency spectrum. There's just so many devices that use radio frequency. Internet of Things is coming. Then we have every device connected to the internet. That is going to place a lot of pressure on the radio frequency spectrum. So that's why we need to think outside of the radio frequency spectrum. So also VLC is an attractive option there. It's fast, it's secure. That means if you have light here, somebody in the next door cannot see it. So that means your data is secure in here. Then it's directive, it's very directive. Light has a well-defined footprint. So it's very difficult for somebody to jam it. Unlike radio frequency, it's isotropic. So anybody can say it. But here it's very focused and directional. There's no EMI, electromagnetic interference. It doesn't cause it. So it's good. And the spectrum is huge on license. And then it adds value to lighting fixture. And a lot more reasons why people do research in this area. So, potential applications, unlimited actually. Very wide. It can be in smart lighting, in smart city, anywhere where there is light. We can think of an application anywhere where there's light. In defense and security, in mobile connectivity, underwater aviation, location-based services for navigation indoor. Actually, this one is now being deployed commercially. There's a shop in France where you can use this one with your mobile phone, put it under the light. It's going to tell you where you are and will tell you, what you have on the aisles. Right? So that is being used now. It's being deployed, and then intelligent transport system and many more application areas for visible light. So the LEDs that are used for visible light, they are mainly for lighting. That's what they are meant for. That means they are optimized for lighting, but not for communication. Lighting requirements are different to communication requirements. So there's a conflict there, and that is where research comes in. You see, they have wide divergence angle. We don't have the frequency response. They are not available. If you look at the data sheet for the LEDs, you don't see anything that has to do with communication, right? The response time is high. We have low modulation, and we have to think about multipath. propagation, and also resource allocation. If we have multiple people, how do we share that bandwidth? That's also an open research. And then configuration. Essentially, this is key. At the receiver side, the SNR, the signal to noise ratio, is inversely proportional to range to the power of 4, right? That limits VLC to short range. You understand? So if you increase the distance by a factor of 2, right? That means your SNR goes down by a factor of 16. So that is huge. So that is why it has to be short range, few meters. It's almost impossible to do VLC for kilometers. You know, it's got to be few meters. 10 meters, that's about it, right? For, you know, indoor lighting. So as I said, there are 2 sets of requirements. LEDs are meant for this. High brightness, right color temperature, you know, high current to achieve good efficiency, wide angle. If you do communication, this is what you want. You want high modulation bandwidth, you want flat frequency response, and you want short response time. It has to be quick, so you can turn on and off. But now you can get this because that is what they are meant for, but you don't get this because the LEDs are not meant for that. You see? So because of this problem, there's huge scope for research. It's a problem for the industry, but it gives opportunity for researchers to work on. So that is why we have things to do, because these ones are challenging. So a typical LED, this is the one I use a lot in the lab. So this is from Osram. The typical LED, you know, it's got small blue components, and then it's got this sort of spectrum. To make it white, it's essentially a blue LED with yellow phosphor on top of it. And then it has this spectrum. This is, I think, is a warm LED because it has little blue. So it's the warm LED, and that is how it looks like. So if you look at the response for that particular LED, this is what you get. If you send a pulse through, you see, it's very slow to respond. And that is because of the phosphor. The phosphor has a response time in milliseconds. If you turn it on, it's going to take about 5 to 10 milliseconds for it to turn on. And that's why you have this slow response. If you put, because it is a blue LED with yellow phosphor. So if you somehow get rid of the yellow, so you can get just the blue. So to do that, we use a blue filter at the receiver. So if you put a blue filter there, then it becomes a bit better in terms of it's a bit faster. Because now you reject all the yellow, and then things become a bit faster. That's what you do to increase bandwidth. That's one option of increasing bandwidth. If you do that, and you measure the response, it becomes this red one, without any blue filtering. You can see the bandwidth at 3 dB is just about less than 3, about 2.5 megahertz. But if you use blue filtering, as we put a blue filter there, then you can get something up to 20 or more than 20 in terms of bandwidth. Now, the amount of bandwidth you get is a function of the drive current. This one, this is at about 300 milliamps. If you change that drive current, then this bandwidth is going to change. And as an illustration, again, the bit rate is a function of all of this, so that's fine. That's the bit that you can get. So if you change the drive current, and measure the 3 dB bandwidth with blue filtering, this is what you get from this LED. Alright? So this can go up until about just under 30, just about 30 megahertz from this particular LED. And 30 megahertz is huge in terms of white LEDs. It's huge, but it has to be at about 500 milliamp to get that. Okay? So that's the device that we use. Now, if you want to increase throughput based on those constraints, bandwidth is small, the response is not flat, then how do you increase throughput? One way is to combine that with higher order modulation, that is QAM. I guess everybody is familiar with QAM. Right. So we want to use high order QAM with multicarrier modulation. And then because the response is non-flat, then we can use blue filtering to make it at least a little bit flat. If you look at this diagram, see, this is not flat at all. But with blue filtering, it's a little bit better. So that's what we want to do. So this is the system architecture that we built in our lab. We use an FPGA board to implement the OFDM using MATLAB. We use system generator to control the FPGA board. And then we put an application on top. This could be anything. It could be video, it could be audio, whatever you want to do. And then we send that to MATLAB. We do it over Ethernet, right? And then we have FPGA board here, digital to analog converter, analog to digital converter. This one goes to our transmitter. Then through the channel, then we receive it. This is the blue filter. Here we have lens, blue filter, and then we decode. The one we get, we send it back to recover our data. That's a very simple architecture that we built in the lab to test, all these things that we're talking about. So this is how it looks like, the physical thing. We put everything in a lamp, right? So this is the lamp here. Inside, here, somewhere here, we have the transmitter. And this is the LED, I showed you earlier. And this is the lens for the LED. The black big stuff here is the heat sink, obviously. And then this is the driver circuitry on top of that. The power supply for that is here. Okay? You connect it from here, there's a cable that goes there, the power supply. The receiver side is inside the box. You can barely see it. You can just about see the receiver. There's a hole at the top here of the box where the light can go through. So the receiver is here. That's very tiny. That's just the receiver circuitry inside. The little glass here is our photo receiver. It's a pin diode. It's not APD, it's the pin one. It's just a pin one, and then power supply. This is the FPGA that we use for the implementation. And that's all. It's quite simple. We put in a box so that we can take it about, we can take it around to show as a demonstrator. So if you do that, that is the specification. A maximum of 256 subcarriers. This up to 256. We don't use all of them because we can only use a maximum of 128 because we have to do emission symmetry. What this one is all about is, remember we said it has to be real bound and it has to be unipolar, right? So to make it real, we have to we have to do emission symmetry. And to make it unipolar, we add DC. So we call it DC OFDM, right? And then the range is about 1 meter. We use the Ultra 23 megahertz bandwidth, as I showed before in the slide. And then the received SNR is about 24 dB. And there's no forward error control, no coding at all. Everything is raw data. That's what we do for the system. And if you do that, we get the constellation for 64 QAM. Just 64 subcarriers here. This is what we get. This is what you get. And from this, the bit error is about 4 tangent per minus 3. This one was achieved some time ago. We have something a lot better than this. But this is our first step of getting the work done. So if you think about the bandwidth from about 2.5 from that LED without blue filtering, 2.5, then we got about 123 megabit per second. And I think that is, at the time, this was the highest that was ever possible at the time. This was about 3-4 years ago when we did this one. And what we observed was, from that, as you increase the subcarrier, the number of errors per subcarrier, for each one of them, you find number of errors. This one, number of errors, this one, number of errors, and that's what we plot here, yeah, for each subcarrier. So, from 0 up to here, no errors. But as you increase the subcarriers, we get a lot more errors. That means the subcarriers around here, where the frequency response is not flat, you get a lot more errors in there. That's expected. It's not a surprise. And that's why here we only use 64, right? Because up to 64 is still okay. The error is still fine. So that's what we've done in there. And because of this problem, we could only get just about 100 megabit per second. And I'll show you how we can even get a bit more from that. So we use that to design like a demo. It's possible you've seen this demo before. I apologize, but if you haven't seen it, but this system I described here, that's what we used to build this demo. And I'm just going to try and see if I can bring the demo up. I guess that's the audio. Yeah. That's that same lamp that is up before. And just send it through. And that video is just going through the light. So when he put his hand there, everything is just going to stop. And that's just a short demo to show, to show our test bed. So if I just stop this one. So that was just a short demo to show what we did with that system. Now, moving forward, we got 100 megabits. But if you want to get something higher than 100, then, if you want to get beyond 100 megabits per second, what do you have to do? Well, what you have to do is, you need to fight this, right? For the high subcarrier, you need to deal with this somehow. And the best way to do that is through this technique called bit and power loading. I guess some of us might be familiar with what that means, bit and power loading. For those that are not familiar, what it means is this. Here, we have so much errors. So that means I'll send little bits here, not many, a few bits here, but I'll send a lot more here, where I have no errors, right? So for the early ones, I'll send a lot of bits, maybe 64 QAM, maybe 128 QAM, maybe 256 QAM. But in this region, where I'll send maybe just 2 QAM, QPSK or BPSK. So I'll get less error because they're going to be few. But here, the channel is very good. I send a lot more. That's the idea behind bit loading. So that's what we do. So bit loading experiment, well, as I said, if you look at the red one, that's the response, the SNR of the system, okay? That is the response of the entire system, end to end. So where the channel is good, here is high SNR, then I send so many 8 bits per symbol, that's 256 QAM. Then where it's not so good, I send 7 bits, 128. Here I go down. Where the channel is bad, here, right? Where it's bad, I just send nothing. Where it's bad, where it's not so good, somewhere around here I'll send just BPSK, and then QPSK, and so on and so forth. That is bit loading. That is, all the subcarriers, they don't have the same constellation. They are different. It depends on how good the channel is. That's what we send. That's the idea behind bit loading. In bit loading, it means we don't just use the 3 dB bandwidth, right? We don't just use 3 dB bandwidth, we use everything. All we just do is, where the channel is bad, we use very few bits. Where the channel is very good, we use a lot more bits there, and that's bit loading. So the advantage is we can use the entire spectrum, not just 3 dB spectrum. So we use everything that's available. And then we do a bit of power loading. That is, you can boost the power here a little bit, like pre-emphasis, like pre-equalization. You give more power to the side because it's low, give more power here. Because this is high, you give less power. So that you want to make everything a bit flat, if you like. So that's the idea behind it. So if you do that, bit loading, then you can have something like this. You can have gigabits. You can see you can have gigabits per second. If you don't do bit loading, this one, here, is everything the same. All of them, the same number of bits. All the subcarriers, same. Yeah? If you give them all of them same, you see, it's not so good. It doesn't even get to 10⁻³ bit rate. That's the one that will go down. If it goes down this way, that will go to about 100 megabits per second, the one I showed earlier. But if you want to get gigabits, then you have to do the red one, which is adaptive bit and energy loading, this one. You do that, then you can get to 10⁻⁴ at about 2.8 gigabits. 10⁻³ at about 3.1 gigabits per second. That is for a single white LED. And if you want more details about this, it's in this paper here from our lab, just in 2014. This is fresh, 2014, not so old. And these are the constellation diagrams, to do that. You have to, if you don't do bit loading, there's just nothing, no way to get gigabit per second. Okay, so that's what is doing that. So for this one, 3 gigabit per second is possible at less than 10⁻³ bit error rate. There are still some issues to deal with here. We have, because we use OFDM, there's this problem with the peak to average power ratio. I'll talk about that in a little while. Also, LEDs are not linear. Lasers are better in terms of linearity, but LEDs are not. So those linearity effects and this high peak, those are the things that are limiting the performance there. We can find a way to correct these two, then we can even go higher than 3 gigabits per second. So that is the limiting factor. So, in terms of challenges, I've mentioned just two. Well, non-linearity is a problem for OFDM or for multi-carrier as a whole. Synchronization, we need to think about synchronization both for the frame and at the symbol level. How do I know the start of my frame? If I start to transmit, how do I know I'm transmitting? So we need to think about that. And high peak to average power ratio for OFDM. And of course, high processing, then we can do something else. I'm involved in this one a lot, and I'll talk about it, high peak to average power ratio. There's a technique that I devise that I will discuss with you in a little while. So, other options for gigabits, well, you can use RGB LEDs, that is, you mix red, green, and blue to make white. And then you can do WDM with all of that. Also, or you can use laser lighting. You can use, instead of using LEDs, you can use laser with lenses, to expand the beam. So people have been doing that as well, and that's also an option. So in terms of non-linearity to the LED, if you look at the typical response curve, or the transfer function for an LED, you get light output, the total number of flux against the drive current. It looks linear. But actually, when you put a straight line on it, it's actually not linear, and that's a problem, right? And this is just a simple approximation. Even within here, that looks linear. If you zoom in, you see also that it's actually not linear, and that's an issue when it comes to OFDM. It's a big problem when it comes to OFDM. Also, that's fine, right? And that also changes as a function of temperature. So that is why thermal management is important. You need to have the appropriate thermal management. Heat sink, fan, and so on and so forth. So because, you see, that's also not linear. It affects performance. So why does that matter? Why is it important for you to make? Well, if the system is not linear, remember we said for OFDM, these are orthogonal. If they are orthogonal, there's no crosstalk. They don't interfere with one another. If you introduce non-linearity there, well, you lose that advantage. There's going to be crosstalk from F1 to F0 and from F1 to F2, and that affects performance. So that is why non-linearity is a problem. We have distortion, we have poor SNR, and at the end, we have poor performance because of non-linearity. So, the more bandwidth you have, the greater the problem. The more subcarriers you have, the greater the problem. And the higher the constellation order, the higher the problem. You see? So these are the things you need for high data rate. And these ones, they suffer more from this effect. You see what I mean? So that's why, we have to do something about non-linearity. A lot of options are being done. People do pre-coding. That is, you code your data at the transmitter, knowing fully well there's going to be distortion in the system. Or you do pre-equalization, and so on and so forth. So, this is one of our systems with just 32 QAM with non-linearity and noise. See, you can see, if you look at this point, it's a bit rotated, yeah? You can see this twist. And then you can see this twist from here, from all of them. That is because of non-linearity. That is causing distortion. It's twisting the constellation. So that's what you get. That means we have to do some processing, equalization. So if you apply equalization, it becomes a bit better. Yeah. So in this one, we've been able to correct for the non-linearity, but the effect of noise is still there. That's why we have cloud. Ideally, in an ideal world, this should be a dot. It should be just one point. But because of noise, we have this little cloud there. We've managed to remove the non-linearity effect, and we could get as low as -1 at this bit rate, for this particular one. What about the second issue? The high peak to average power ratio for OFDM. Well, this is OFDM, right? As it is. Why do we have the high peak to average power ratio? Well, what happened is we have this one, F0, is a sinusoid. right? F1, F0, F1, another sinusoid, but much faster. And then we have F2, which is also much faster. If you look at N, if you continue, at some point, it's possible for all of them to add up coherently. They can all add up together. So all the peaks can align. So it becomes high peak, right? So that is the issue. That is why that is a problem. Here, it's possible for all these ones to add up coherently. So we have a huge peak in the signal. If that happens, if we have high peak in the signal, see, this is our response for the LED. Here, it's saturation. The LED saturates. It's not linear at all here. Here is 0 point. Anything below 0, there's nothing. It's going to cut off. And your OFDM signal looks like this. You see, it's got high peaks everywhere, like that. So it's possible for this region to be in the saturation, right? So this region is going to be heavily distorted. There's going to be a lot of distortion around this red. And here is below 0. You see? So there's going to be a problem because to use LED, it has to be real and positive. But this is already going to negative. You see? Why is that? Because of the high peaks, because the signals can add up. So that is the problem. That is an issue. Not just for optical, also for radio communication. What is done normally is just to clip. You just cut this one off, forget about it, cut this one off, and then that's it, and hope for the best. But clipping is not the best, and I'm going to show you why that is the case now. So this is a big issue for OFDM. Well, again, I said, make sure LED to go into saturation, and that causes signal distortion. You can clip your signal, but when you clip, you lose something in terms of performance when you clip. So, a typical OFDM signal is Gaussian in distribution. It should be. This one should extend all the way, because this one was produced in MATLAB, so it's limited to about 0.3. But in reality, it should keep going, and it should keep going. Everything is right in the middle, about 0. But you do get these occasional peaks at the end. And you do get these ones. And those are the problems, for OFDM. If you work out the peak to average power ratio, that is, the peak here as a ratio of the mean, you get something like that for the distribution. So it goes from about 8 dB to about 14 dB for this particular example, right? That is just an illustration. Let's keep this in mind. That's what you get from this particular example. You can clip, as I said. See, I don't want this end. They are too high. So what I can do is I can clip. Just cut it off at 2.1. Cut it off at minus 2.1. Why? Because I want to keep it within the dynamic range of my LED. I want to keep the signal within the linear part of my LED. So if you do that, well, this is what you get in terms of performance. If you don't clip at all, if you use all of the signal, this is the beta rate performance, right? So you can go as low as you want. But by the time you clip, then it comes to this, it gets to the error flow. That is, it can never be better than 10 to the power minus 4. You see? That is a limitation. That is, the performance gets worse. If you want an ideal optical system, you have about 10 to the power minus 9, beta ratio. But this can never get there, 10 to the power minus 4. So that is the penalty. This error flow is a function of where you clip. If you clip here, it's even going to be higher, right? If you clip here, it's going to be lower. But there's always going to be a penalty when you clip. So that is a problem with clipping. So because clipping is not always good, we have to do something else. So what can we do? Well, there's a technique that I introduced. It's called the pilot-assisted technique for PAPR. What does it do? Well, I'll explain very briefly how it works. Essentially, you have all of these ones, OFDM, here. These are my data symbols. OFDM in frequency, in time, in time, in time. So I have a frame of OFDM symbols. All the white ones, these ones, my useful data. Then I put a pilot in at the end. And normally, when you do transmission, you put pilot there to estimate the channel. Once you understand the channel, then at the receiver, you use your pilot to do equalization. It's always going to be there anyway. So we use the same pilot, and then give the pilot, each one, a random phase, right? Random phase, random phase, random phase, random phase. So for the ones on this line, I use this phase to multiply all of them. For the one here, I use its own phase to multiply all of them, and so on and so forth. That is, I rotate the phase of my symbol with that of the pilot. Why do I do that? Well, remember, if all of these ones are coherent, this peak, this peak, this peak, they can add up. It becomes high because they're coherent. But if I put a pilot there and I change the phase of this a little, so I introduce, let's say phi 1 here, I introduce phi 2 here, and this one phi 0. If they're all random, then there's a high possibility that they don't add up. So I can move this one slightly so it comes here. I can move this one slightly so it comes here. So they don't add up anymore. That's the whole idea. So I want to make sure I destroy the coherent addition. How? I just rotate the phase. See the point? So that's the whole idea. Wow. What did I do? Okay, sorry. So that's the whole idea here. I just rotate the phase to make sure they don't add up coherently. That's the whole idea. So if you do that well, as I've explained, this is my data symbol, this is my pilot. And I use my pilot to multiply my data such that I can change the phase a little bit. And then I work out the peak to average power ratio. It's going to get smaller because I use random phase. Yeah. So that's the whole idea. If you want more details about this, you can find it in this paper in 2014. Light with technology. So it's there. So if you do that, remember this, normal OFDM signal, in time domain, it should be Gaussian. In time domain, it should be Gaussian. If you use the pilot assist technique, it's no longer Gaussian because you change the phase. Everything is moving around. So it becomes something like this. No longer, a full Gaussian signal. And that is good because it doesn't, it destroys this coherent addition in there. And if you look at the PAPR that I showed earlier, remember it was about 8 to about 14 for the PAPR. If you apply that technique, the pilot assist technique, well, it takes it down from about 8 to about just over 11. So that's about 3 dB that you get just by changing the phase. That is significant. For 3 dB is half the power. So that is pretty significant and what we managed to achieve with that technique in gate. It gets better when it comes to the error performance, or this is the CCDF for the performance. If you don't do anything, your basic OFDM is like that, right? So what this one means is that, as it is here, 3 OFDM frames out of every 100. If you take 3 frames out of every 100, the PAPR is going to be more than 12.8, right? 12.8 is somewhere here. So that's what this one means. 3 for this one, 3 out of every 100 will have PAPR that is more than 12.8. If you apply the technique, it goes to 1 out of every 10,000. So that means the chance of the PAPR being greater than 12.8 is quite low, very, very low if you use the technique for 64. And we can see that with the diagram. Here, without the basic, ordinary. And then when you apply the technique, it goes all the way down to that. Okay? So that is what we gain from using the pilot assist technique. In terms of error performance, I showed earlier, if you click, it gets to the error floor. If you don't do anything, it goes down. If you use the pilot assist technique, it's exactly, almost identical to the ordinary. The only penalty is here, where you have low SNR. Around here, it's a small penalty because they're not the same. But this is fine, because for every communication, you want to be 10 to the power minus 3 and below. And that is where it's a very good match. So that's not a problem at all. So that is what we gain from doing, and that is just the explanation of what I've just been talking about. So that is the pilot assist technique to correct for peak to average power ratio. Again, this is just to illustrate, depending on where you click, you see this is 2 clipping. If you click both levels, that is you click to avoid saturation, and you click at the bottom, then you can have a terrible one. But if you click in one place, just once, then you have this one. And then this is the pilot assist for, almost exactly the same thing as what we get for that one. So that is the technique that we introduced in our lab. So to summarize, or in the way of conclusion, you see, what we're saying is, if you want to get about 10 megabits per second, you don't have to do FDM. You can just do simple on-off keying. That would be good. You can get 10, 20, 30 megabits per second with a single white LED. If you want to get hundreds of megabits per second, well, you might start to consider OFDM. You might have to consider blue filtering, as I mentioned previously. If you want something higher than that, you can see the processing or the complexity is on this axis, right? So if you want something higher than that, up to 3 gigabits per second, well, you might use single color LED. Instead of using white, that's a mix of blue and yellow, you might use just blue LED, because that gives you higher bandwidth, right? And then you can do equalization with OFDM, bit and power loading. You can get 3 gigabits per second, as I showed earlier. If you want something higher than that, right, then you can use single color LED, equalization, OFDM, bit loading, plus PAPR power reduction that I just described. If you want something higher than 3 gig, we've got something like 100 gig in our lab, 100 gigabits per second. Then you have to do this. You have to use laser if you want to get to 100. In some cases, you can get close, like 50, like 40 if you use RGB LED with WDM as well. Then you have to do a lot more processing. There are more techniques that perhaps I'm not aware of, and some that are still, working, people working on them in their lab that maybe I don't know about. So there are a lot more options out there to get to 10 gigabits per second and a lot more. So thank you so much for your attention, and happy to take questions if you have any. Thank you.
Thank you, Professor, for your very interesting lesson. And now we may open a discussion.
Yeah.
Colleagues, please, if you have some questions.
Questions, comments?
Comments to listen to this lesson. I have one question. What do you think about laser lightning and communication at the same time? Yes. Because I think that it is a problematic view from the point of our eyes.
Yes.
Because our eyes are suitable for incoherent lightning, yes, not for coherent lightning. Correct. Do you think that these will be some problems?
Potentially, yes. Potentially. So what people try to do is, because there is this safety standard, you are right, because of the eye safety standard. So if the beam is collimated and coherent, that is dangerous for the eye. So what people do is to destroy the coherence and destroy the collimation. So you make it bigger. So people use lenses to diffuse the beam. They use expander lenses to make it bigger and destroy the coherence. That's what is being done. Whether it's going to take off is a different question. In automobiles, for instance, in cars, I think in Audi or BMW, they already use laser lighting with a lot of lenses. Yeah. So if it takes off there, then maybe people might be convinced, to use laser for lighting. But yes, safety is a big concern. It's a big one. Yeah.
Thank you. Another questions?
Comments? Question? Do we all converse? Yeah.
What about distance for communication? If you have a huge amount of data which you want, then distance should be lower.
Yes, the short, as I said earlier, the SNR is a function of the range to the power of -4. If you have high or good SNR, you can have huge data. So you're right. So distance has to be short. So you need to have a compromise between range and data rate. If for the experiment here, if you read any paper talking about 100 gigabits per second, check the distance. It's always going to be in, at times, less than a meter. Most of it. The one we've done in our lab was around here, about 3 gig, for about 10 meters. And that was using laser, 3 lasers, red, green, and blue. So that we can go on it. With lasers, yes, it's not a problem. With LEDs, it's got to be short distance. Yes, you're right. Okay. Yeah. Any more questions, comments?
Do you think that for the future, will it be possible to combine power line systems and lightning and communication together? Because today's structure of power line systems is not suitable for a higher bit rate.
Yes.
And from my point of view, it is a very good potential advantage for this technology. But now I see more problems than advantages. In fact.
Absolutely, I think you're perfectly right. Because the power line is already there on the ceiling, and then the lighting is just going to take it down. So naturally, there should be a synergy there. For VLC, it's not just all about this data rate. Actually, the early applications might be here. In the standard, the standard goes up to about, I think, few megabits per second, but not gigabits per second. So if we are looking at applications around here, few tens of megabits per second, yes, you can work with PLC, because PLC is not so high, you see. So that is a possibility. And there are a lot of talks and collaboration between different labs and power line communication. Yes, that is a natural path to follow, definitely. For low speed.
Yeah, thank you. Another question?
I want to ask, you will need for some room more sources. What do you hand over? Could be this problem?
Yes, handover is an issue that has to be solved. What we do is, in our lab, we do research, and then we have like a company, a spin-out company. So in the spin-out company, they've done something with handover. Most of our lab, work in the lab is physical layer. So in the company, they've done something in the mark layer and above. So they've done some handover. But I'm not entirely clear the method they've used, right? I don't know exactly how they've done, but they've done handover. And there is also, I think there's a video of it. So you just move around and it transfers you straight away. So it's a problem, but I think that's a solution for the handover. Yeah. So it's been done. One option, the easiest option, is to use frequency. Use wavelengths as you move around. So that's the easiest option. Or you can also use CDMA, it's possible. Or you can use, there's this common one, non-orthogonal multiple access, where you use power. Different user, we have different power allocated. And as you move around, then you can have more multiple. Yeah. So that's also an option. But in terms of experimentation, the company has done it. And I can send you the video if you want. For the implementation, hardware. Yeah. So that's an option. Any more questions?
One question, maybe the last. Power LED are known that the aging of this device is very quick in comparison to normal standard LEDs with middle or low optical power. Power LEDs, do you think that the lifetime of these communication systems is long or short in comparison to communication systems with mid power LEDs or low power LEDs?
I think that's an important question, because my talk in the afternoon we touched a little bit about that. The problem with LED is, if you look at an LED, they tell you the lifetime is, some will say 50 years, some will say 20 years. When they fail, it's not usually, the good ones, it's not usually the LED, it's the electronics, the driver. Those are the weakest link there. Right. For you to get the lifespan, there are two things that are important. One is the drive current, right? And the other one is the temperature.
Yeah.
So for temperature, use good thermal management. For the drive current, for as long as you are within the spec, the manufacturers will tell you what the drive current should be. If you're above it, yes, you risk the life of the LED. But if you are within the specification, it should be fine. We've been using, we've not been using them for 20 years, but we've been using them for so long, for about 6-7 years now, constant, almost all the time, and they are still working fine. So for as long as you are within the stipulated coil, the recommended coil, then it's okay. And you use good thermal management, that is fine. What I will talk about in the afternoon is light quality, right? If you put light in here, they are meant to give a type of color, whether it is cold white or warm white for certain application. But by the time you add VLC onto that light, what happens? So, you know, there's a big debate about that because the lighting manufacturers, they care about light quality, but they don't care about your VLC. So that's one other research area that I'm looking into, and I'll talk about that in the afternoon.
Thank you.
Excellent. Any more questions? Comments?
Is there any limitation of devices that can perform in, for example, your one lamp as you show in the demo?
The answer is no. For as long as it's LED light, no. All we have to do is to do the characterization before you design. So we have to understand that LED, and then we can use any LED.
It will be in the spot, actually.
Yeah, we can use any LED. Or we just have to understand the properties, the bandwidth, the response, and so on and so forth. And then it's fine. Is anybody working on the visible light here?
Yes.
Yeah, so what's your interest in visible light?
So I'm working on RGB light photo.
Yes.
So I have red, green, blue, and yellow.
Yeah.
So I'm trying to use this in my.
Are you trying to implement some modulation technique or?
This, I'm more interested in supporting of more users in the area.
Oh, okay. So multiple access. Yeah, okay. Yeah. That's an interesting one. So we also use RGB as well. Just three, not yellow. We use RGB. So how do you find them? Is it difficult to use?
Not difficult to use, but difficult to create, manufacture.
Yeah, okay. Do you manufacture them?
That has to because no manufacturer work with.
Okay. We tend to use off the shelf. We just buy from the shop.
Well, I have to buy separate lights and then.
Okay. There are some that they come together, like a single chip. You know, just one device with red, green, blue, and yellow.
Yeah.
So we just buy from the shop and then just use it.
I didn't find them yet.
You couldn't?
No.
Okay.
Maybe I will.
Yeah, I can send you some data sheet, some part number, then you can find it. But we just buy from the shop, straight away. Anyone else? Visible light, what do you work on?
Yeah, I work with the episode
Yeah.
outdoor, and I'm trying to find some way how to describe the atmosphere, like a medium.
Yeah.
That's what you're thinking of.
Yeah.
And I'm trying to simulate in flow also the waves and the temperature gradients and what?
Turbulence, scintillation.
Simulation.
Yeah. Okay. So which model are you using? Are you using the log normal, the gamma?
Yeah, I'm using the model for the flow of the gas.
Okay.
And that's the K-epsilon model for the flowing, and the true ones make the true ones. It's about a little bit about the flow and liquids dynamics.
Yeah. Okay. Okay. That's interesting. And yeah, so that's what we do. If there are no more questions, I'm still around, you know, for discussions, or if you think of any question later on, you can still ask me. So let's say thank you so much for your attention.
Yeah, thank you again.